Okay, so we're going to look at the June 2005 Unified Physics paper. So the mathematical term proportion is used a great deal in physics to describe certain situations, and particularly how one quantity varies with another. So answer the questions in the table and explain under what circumstances the relationships correctly do show direct proportion. The first one is done so we can see what they mean. So we've got the equation S equals ut plus half at squared, and the question is S directly proportional to t? So your instinctive reaction should be no, because there's a t squared in the equation to start with, but it could be a directly proportional relationship, but only on the condition where acceleration was 0, so the half at squared term disappears, and u would be constant in the scenario you were looking at, and then S would be directly proportional to t. Okay, so let's have a look at a few more. So starting off with the V equals U plus AT. Is V directly proportional to T? No, that equation shows what might be a linear kind of relationship, but it would be directly proportional if U was 0 and A was a constant. Okay, so then next one, PV equals nRT. Is pressure directly proportional to temperature? No, not particularly. It could be if temperature was measured in Kelvin and the volume and the number of moles were a constant. Under those precise conditions, yes, it could be directly proportional. P equals FV. Is power directly proportional to force? No, it would be if V was constant, but if V was constant in most scenarios, the power and the force would be constant as well. So I would say no. And then area is pi r squared. Is area directly proportional to r squared? Yes, because pi is always a constant. Okay, so to finish off this question, which features of a graph plotting one variable against another would determine whether two variables are directly proportional? Well, it should be a straight line or have constant gradient, and it must pass through the origin as well. Okay, so moving on to question 2. In the following situations, explain the physics of why there is always a strong wind near any forest fire. Okay, so first we have to think about what happens to the air right next to the fire. So the air around the fire is with temperature will rise, and because its temperature rises, it's going to expand and become less dense. And because it's less dense, it's going to experience a upthrust or a buoyancy force pushing it upwards. So we're just using Archimedes' principle. So that's why hot air rises, its density goes down, so then it experiences a net force upwards. So then what happens is cold air moves in to fill the space left by the rising hot air. So that comes from outside, and that's the source of a wind. And this whole process creates what we call a convection current. So you get the hot air going up just above the fire and then cold air coming along the ground to replace it, and you've got a convection current. Okay. So how is it possible to have a shoe which is both shiny and black? So if you think about it, those two processes are essentially polar opposites of each other. So shiny means you reflect light, whereas black means you absorb all of light. So they appear to be polar opposites. So the shoe must be made of two materials, one which is black and absorbs light, and then there's a layer on top which can reflect some of the light, which makes it look shiny. Why the tension in a string of an oscillating simple pendulum is not equal to the weight of the pendulum bob when the string is vertical. So the first thing you have to recognize is when the string is vertical but the pendulum is swinging, the bob is accelerating upwards towards the pivot and is not in equilibrium at this position. And then that means the resultant force must be upwards, so the tension force must be greater than the weight force. You could also answer this by considering the fact that the pendulum is effectively in some form of circular motion at this point, and there must be an acceleration towards the center of the circle as well. So that logic could work too. So explain why X-rays do not seem to be diffracted by a narrow slit of width about 0.1 millimeters. So first thing, we need to think about what the wavelength of X-rays is, which is about 10 to the minus 10, which means the slit is about 10 to the 6 times larger because the slit is 10 to the minus 4 meters. So you should know that maximum diffraction occurs when the object is the same size as the wavelength. So if the object is 10 to the 6 times larger, we're going to get pretty much no diffraction occurring. Okay, so why it's not possible to polarize sound waves in air? So the first thing, I don't know why we need all this space, because essentially you can answer this very quickly. Sound is a longitudinal type wave, and you cannot polarize those kind of waves. You can only polarize transverse waves. So explain why keeping a refrigerator door open does not cool a kitchen. So to understand this, we first need to appreciate what a refrigerator is doing. So a refrigerator removes thermal energy from the contents of the fridge and pumps it into the surroundings, i.e. the room, and it does it by inputting electrical energy, which is why you need to plug it in. So if you open the door, the fridge now has nowhere to pump the thermal energy to cool the room down, because it's basically pumping thermal energy into itself. And because the process is not 100% efficient, the act of pumping the thermal energy from one place to another is going to increase the amount of heat or produce heat. So you're actually going to make the temperature of the room hotter by opening the fridge and leaving it there. Okay, so moving on to question 3, looking at some circuitry. So we're looking at the circuit used in a car. So we've got a generator and a battery in parallel. And the battery has very low, the resistance, so we're going to ignore it, and the generator has an internal resistance of 0.5 ohm. And we've got a circuit with headlights and a circuit with side lights that we can see on the right-hand side. And we can see from a switch, we can either choose to have the lights off, the headlights on, or the side lights on with no other options. So first question, explain why headlamps have a lower resistance than side lamps. Well, they need to be much brighter. So headlights need to essentially allow us to see a long distance in front of us, which side lamps don't. So they have to be much brighter, which means they need more power. And that, to get more power, we'd need more current, because all of these lights have the same potential difference across them, but to get more power, we would need a higher current. So explain the function of the three-way switch A. So the three-way switch allows you to either have no lights on by being in the position it's in currently, or if you connect it to either the circuits, you could turn either the headlights on or the side lights, but you cannot have both on at the same time. Okay, the PD across the terminals of the generator must be 12 volts, the same as the terminal PD of the battery. Calculate the current through the generator. Okay, so we can essentially use this equation for linking the EMF and terminal voltage. We know what the EMF is, we know what the terminal voltage has to be, and we know what the internal resistance is, so we can calculate the current. And as to why the two PDs have to end up being the same, that's just so that the circuit obeys Kirchhoff's second law. The sum of the PDs is a fixed value that's determined by what's going on with the light bulbs. So therefore, the sum of the EMFs in any loop must be the same value of 12. Okay, so when the headlamps are switched on, calculate the current to each headlamp. So what we can do is essentially just use Ohm's law. We know the PD is 12, we know the resistance is 4, so each headlamp is going to get 3 amps. So to get the total power to the headlamps, the power would be double the power delivered to just one of them. So that's why there's a 2 in there. And the power delivered to one of them would just be 3 amps times 12 volts. Times by 2 gives us 72 watts total power. Okay, so for the situation we had, assuming that no other current is being required by other car components, deduce the current through the battery and state what is happening to the battery. Well, we've got 2 headlamps, so the current to the headlamps is going to be 6 amps. But we already know to give the 12 volt potential difference, the current from the generator is 6 amps. which means 2 amps must be going into the battery, which means the battery is being charged, which is what is happening most of the time when a car is traveling. So what advantage is gained by using a battery with very low internal resistance? There's a few different ones. So if you have very low internal resistance, even if the current changes quite a lot, you can supply a fairly fixed voltage. You can supply a larger current with a low internal resistance, and you're just wasting less energy generally if you're not dissipating energy as heat in the internal resistance. What advantage is gained by having the EMF of the generator higher than the EMF of the battery? So I'm going to explain this by considering the opposite case. So if the EMF of the battery was greater than the generator, you could never charge the battery using the generator, because the current going to the lights would always end up being greater than the generator current, and you'd end up trying to charge the generator essentially, which is probably going to break it. Okay, so moving on to question 4. A radioactive material is known to contain a mixture of 2 nuclides, X and Y, with different half-lives. We've got readings of activity taken as the material decays, and that's what's in the table. And we've got the activity of nuclide X over the first 12 hours. Okay. So first thing, we're going to explain a few terms to do with radioactivity. So what does radioactive mean? Well, radio is there because it emits radiation, and in the specific types that we talk about being radioactive, it means it's emitting alpha, beta, or gamma radiation. But that's what radioactive means. Nuclide is the notation we use to describe the structure of a nucleus, and it's when we're noting its nucleon number and its proton number. And so if they're 2 different nuclides, that means they've got 2 different notations. Half-life is the time taken for activity to fall to half its initial value, or the time for the number of undecayed nuclei to half. They're the same thing. So now what we're going to do is, we know the half-life of nuclide X is 18 hours, so we're going to fill in some missing data for X and Y. So X I've done just using the fact the half-life is 18 hours. So the 18 hours would just be half the initial one, and then the 24 hours would be half the time at 6, and then finally 36 would be half what it was at 18. Then if we know the total activity of the material, we can just subtract the activity of X to give the activity of Y to get all those values on the right-hand side. Okay, so calculate or use a graph to determine the half-life of nuclide Y. So I'm going to do this by calculation because I think it's quicker. So we know the activity is governed by this exponential function like this. So the first thing we can do is to calculate what the decay constant is. So I used the values at 36 hours and 0. So using those values, I've calculated decay constant, then done ln2 divided by decay constant to give a half-life of 72 hours. But you will get slightly different values depending on which time and value you picked. Okay. So indicate briefly how it would be possible experimentally to attain the initial activity of nuclide X by itself. So one thought I had is they may well be emitting different types of radiation, so you could use some sort of blocking material in front of the detector to absorb one of the forms of radiation. You could also do something like use a mass spectrometer to separate the 2 materials. You may be able to dissolve one of them. There's a few different ways of separating them, but this is the simplest one to do experimentally, I think. Explain why it's not possible to give a half-life for a mixture of 2 nuclides. So the key here is that materials have 2 different half-lives, but we can see from the data that X is initially much more active. So I would say to start with, the half-life would be very similar to X, but towards the end, when X has mostly decayed, the half-life will be very similar to that of Y. But between the 2, we'd have a constantly changing half-life. So throughout the life cycle, if you like, of the mixture, the half-life is going to be changing all the time, so we can't quote one value for it. And this is something you can show using maths as well. You can essentially work out the decay constant of the two separately, add them together to try and figure out what the half-life is, and from your calculation you'd see the half-life would be changing all the time, so we can't give one value for it. Okay, so that completes this unified physics paper. Thank you for taking the time to watch.